Hello, my name is Amanda, and today I will be doing an overview of alcohol elimination reactions. In any elimination reaction, two groups from adjacent carbons are removed and replaced by a double bond between those two carbons. It is the proton on the beta carbon that is removed because if you remove a proton at the alpha position, the electron will have nowhere to go. So let's define what an alcohol is. An alcohol is a carbon with an OH group attached. And since we know what an elimination reaction is and an alcohol, let's put them together. So an alcohol elimination reaction is when an alcohol reacts with an acid. The acid has to be one of these three: phosphoric acid, or H3PO4, sulfuric acid, H2SO4, or tosic acid, which is the abbreviation of p-toluene sulfonic acid, as we see on the bottom. So let's describe the mechanism of elimination reaction for alcohols. The first step is protonating the OH group to facilitate its removal. So we draw from the oxygen to the proton, and this proton represents one of the three acids that we described before, and we started off with a tertiary alcohol. Then this is followed by the cleavage of the CO bond to give the carbocation intermediate. So we're left with the carbocation and H2O, or water. In step 2, we have the water and the carbocation, and this is the deprotonation by a water molecule. So because of the properties of water, it will be used as a base in this reaction. So we go from the oxygen to the hydrogen, and then from this bond over here, from an adjacent carbon atom to the carbocation center, which leads to the creation of the carbon-carbon bond and the alkene. So this is the alkene product, and we're left with a hydronium as well. Elimination reactions tend to follow the Zaitsev's rule, which is to always form the most substituted alkene, meaning we remove a proton from the carbon with the fewest attached hydrogens, because alkene's stability increases as we increase the number of attached carbons. So we're going to look at an example. This alcohol is being reacted with sulfuric acid. So we draw the arrow from the O to the H, and then from the bond to the oxygen on sulfuric acid. And here is our intermediate, and we draw from the bond to the oxygen. Next, we have two different ways to go through this reaction to get different products. In the green stage, we react water with this proton, and then we draw the arrow from the bond to the other bond on this side of the carbon, and then we end up with this product. Now this product is a less substituted alkene, and therefore it's a minor product. In the other pathway for the reaction, we react H2O with this hydrogen, then we move the arrow from this bond down to this one, which gives us two different products. We can end up with the cis alkene or the trans alkene and an additional hydronium ion. Now, for a reaction that can produce more than one alkene product, generally the thermodynamically most stable alkene is favored. So the more substituted alkenes are favored over the less substituted ones. And these are more substituted than this one. So this one is a minor product because it's less substituted than these. Now, our second rule is the trans-substituted alkenes are preferred compared to the cis-substituted ones, as seen in our example. So this one, because it has the trans alkene, it is the major product. And since this one is the cis alkene, it's also a minor product. Therefore, this product is the most likely to occur based on this reaction. So in conclusion, to take off a part of the compound that is a good leaving group, eliminating it, this often results in the formation of a double bond. So we often form an alkene, a carbon-carbon double bond, as seen in the previous examples. In order for this double bond to form, two molecules need to be removed from the two neighboring carbon atoms. Often, one of the two molecules is a hydrogen atom. This reaction can occur as an E1 reaction in two steps, or as an E2 reaction in a single concerted step. The alcohol must react with a specific acid to create the desired elimination reaction, such as H2SO4, H3PO4, or TSOH. The alcohol or OH group is designated as the major leaving group for these reactions. So that concludes this lecture on alcohol elimination reactions.